All right, this is part 3 of the sample exam problems, exam 1 problems for Math 2414 Calculus 2. So we're starting this session off with problem number 29. So we have to solve this differential equation by separation of variables. So let's see what we should do here. We're going to have to get the x's and y's separated. We always like to move the dx up first, and so move the dx up. And the x's are there, but I got this secant y, so I divide both sides by secant y. So we have dy over secant y. As one thing I've mentioned, if not early on in this course, I mentioned it throughout the course, especially with chapter 8. Anyway, is you never integrate like 1 over a trig function. You never integrate that. You must always convert it to its reciprocal trig function. 1 over secant doesn't integrate. 1 over anything doesn't. Trig function doesn't. So what happens is you just change 1 over secant to cosine, just using trig relationships. Then we integrate cosine, and we integrate 6x to the 5th. So the antiderivative of cosine is sine. Antiderivative of x to the 5th, 6x to the 5th, is x to the 6th plus c. Technically, that's actually solved. That's why I have the flag there. But if the question asked to solve it explicitly, if possible, meaning to solve for y, we can do that. So applying arc sine to both sides, arc sine and sine are inverses, so they kill each other, just like E and ln knock each other out because they are inverses. So we end up with y arc sine, and this is correct to write it this way. I know it looks weird. First time you've probably seen an integral that has a plus c inside parentheses like that. That's not normally the case, but in this case, that is correct because you're applying arc sine to all of that, including the c. So, okay. A little strange, but not too bad. How about this next one, number 30? So I'm going to probably cross multiply here, looks like. Yeah, I brought the 8y squared over down this way and the dx over up to the right. And let's see, so we have so we integrate both sides. So you have 1 over 8. So you bring the y up. Keep in mind, you don't bring the 8 up. The 8, because it's not in parentheses. Yeah, so a lot of people make that mistake. The 8 stays right where it is, so it's just 1 over 8, which, you can bring that outside the integral if you want. But we're integrating y to the negative 2 and leaving the 8 on bottom. And the right side, we have the antiderivative of x to the negative 1. So the antiderivative of y to the negative 2, using the power rule, would be y to the negative 1 over negative 1. So it's okay to leave it as a negative exponent, that's fine. But I went ahead and just dropped the negative 1 down and made it positive on the bottom. And then there's the negative from the antiderivative. And on this side, we have ln of x plus c. I don't think, okay, probably wouldn't ask to solve for y on this one, but looks like it, if you did solve for y, you cross multiplied, brought the 8y up, and then you could divide by ln of x plus c, and then multiply the 8. So basically, y comes up, ln of x plus c comes down with the 8. Forgot to close these parentheses off here. So this would be correct like this. Oh. Or that's fine if we're solving for y, or the other version is correct because like I wrote over here, really if you distribute this, c is just c, so multiplying it by a new number doesn't change anything, so 8 times c would just effectively still be c. All right. Now we have an initial value problem where it gives us this condition y of 0 equals 1, and that just means we're able to solve for the value c. So your final answer here will not have plus c in it. All right, pretty easy to separate. You just kind of flip-flop the y cubed and the dx, essentially. So you have dy over y cubed equals dx. So you're integrating y to the negative 3 on the left and dx on the right. So you have y to the negative 2 over negative 2. And I just dropped the y down. I didn't have to. So there's kind of several correct ways to do it. Notice I mentioned do not solve for y here, mainly because of the y squared. So we're going to get this without solving for the y. So it looks like I just tried to rearrange it just to get the y squared by itself. Even then I didn't have to. Because at this point, if right up here, if I put 0 in for x right over here, and I put 1 in for y right down there, so you have negative 1/2 equals 0 plus c, like I have right there. So c is just negative 1/2. So I guess my point being is really, I'll put a little dot right here, you know, technically right there, that would be correct because you've effectively solved it for c. The rest of that's just a little algebra rearranging there, basically. So you see essentially I flip-flop these, 2 times x minus 1, bring that down, and then the y squared up, and then 2 times x minus 1/2 is just 2x minus 1. So I don't know if we had to. So anyway, so at this point it's just a matter of how you presented the answer, so to speak. But here's another initial value problem. So let's see, leave the 2y dx for a minute. I don't want to multiply by, usually my first step is I multiply by dx, but not in this case. It's because I have that minus 4xy, so I don't want to do that. I want to move the 4xy over first before I do that. So you see I added it to the right side now. Okay, so now we have it. Now I can then bring the dx up. And this is important, so I factored out a 4x from this, so at least 4x times 2 plus y, and then I simplified. I could have waited till later, but I went ahead and did it now. 4 and 2 share a common factor of 2, so it's like dividing out 2 from both sides. And then once I have this 4x and the 2 plus y factored out, I then divide both sides by 2 plus y. And that will enable me to get, so then you see the 2 is now gone, so now I have it separated. So I have dy over 2 plus y, and then I have 2x dx on the right side here. And now we integrate. So the antiderivative of dy over 2 plus y would just be ln of the absolute value of 2 plus y. The right side will be x squared, so it's x squared plus c. So if we're trying to solve for y here, if it asks for that, we e both sides. So if you e both sides, you have 2 plus y. I didn't worry about the absolute value. Equals ce to the x squared. We talked earlier about that c in another group of problems. Anytime you have that plus c where e is being raised to it, it always puts the c in front. And you can look back at my notes for that too. So I'll bring the 2 over. So here's the general solution for this problem. Y equals ce to the x squared minus 2. So if we didn't have that initial condition, y of 0 equals 12 would be done. But now we have to use that, though, to solve for c. So you put 0 in for x, and you put 12 in for y on the left. So 12 equals ce to the 0 squared minus 2. Well, e to the 0 equals 1. So that leaves you with 12 equals c minus 2. Add 2 to both sides, so c would be 14. So the final answer, this particular solution it's called, because it gives this initial condition, is y equals 14 e to the x squared minus 2. All right, now we've got a Newton's law of cooling problem, and that formula is on the formula sheet. Oh, okay. I guess I didn't have enough room to put it up here, but there it is right here. So you set this up as, the model sets up as whatever the ambient temperature, in this case the room temperature, goes here, and the constant C is actually works out being the difference of the object temperature when you remove it minus that room temperature. So that's always the case for this. So it's 70 plus 350 minus 70 e to the kt. So that'd be 280. So now we know that it's going to be how long it's going to take to get to 210 degrees in that 70-degree room. So this will help me solve for the K value. So I know that when T is 20, so it's e to the 20K, Y will be 210. So if I bring the 70 over, and looks like I sort of skipped a step here, but anyway, if you bring the 70 over, that makes it 140. Then when you divide by 280, 140 divided by 280 is 1/2. So you have 1/2 equals e to the 20K. Now we natural log both sides to get rid of the e. So you have 20K equals ln of 1/2. So K equals ln of 1/2 divided by 20, which you see over here. I did in the calculator. I usually put 4 decimal places. I usually say use 4 decimal places. And so that means so now the K, so the model will be, this model K being negative 0.0347 negative times T. So then we're trying to say, I can't read that, but obviously you can on the original file. How much longer will it take to cool to 140? And so it's already gone 20 minutes, so be careful with the wording on this question, because I've been known to do this on a test. So what we're about to solve for is the total time, but that's not what the question's asking. It's question's asking, all right, you solved the total, but then how much was that time beyond the initial amount of 20 minutes? So we have 140 is what, we're trying to find how long it takes to get to 140 equals 70 plus 280. Now we have the e. So I subtracted 140 minus 70 is 70. Then when you divide by 280, so 70 divided by 280 is where that 1/4 is coming from. Now we natural log both sides, and that kills the e. And you see in the calculator, I did, I used all those decimals there instead of rounding it. But anyway, basically that's ln of 1/4 divided by this, but it's using more decimal places, which surprisingly generated an exact answer, which is shocking, but usually it's a decimal answer. So what we're saying here is that means it took 40 minutes for the bread to get down to that temperature. However, that doesn't really answer the question. That means the answer is how much longer it's taking is 20 minutes. In other words, 20 originally plus another 20 makes 40. So that second 20 is what the answer to the question is. I should have, I'll do it right now. Let me move this out of the way. I'll put a flag here next to the actual, not the total time, but then the part that represents the answer. Okay, lower that down just a little bit so it's by itself. There we go. So the 40 minus 20. Okay. Here's another Newton's law of cooling. So it's hard to read those numbers again, but the freezer is 0 temperature, so there's the zeros coming from right there. This is 104, so it's always 104 temperature of the object minus the environment temperature. So we're shoving in there. So it's 104 minus 0. So it ends up being 104. And so we have y equals 104 e to the kt. So it says in 5 minutes, it's already down to 70.1 degrees. So that will help us solve for k. So 70.1 equals 104 times e to the k times 5. So you divide by 104, natural log both sides to get rid of the e. So we have then k equals ln of 70.1 divided by 104. All that divided by 5, which you see here is in the calculator. Approximately using 4 decimals equals to negative 0.0789. And so that means your official model then is y equals 104 e to the negative 0.0789 t. And then it says, what will the temperature be 20 minutes after it's placed in the freezer? So this one's not asking additional time or anything. It's just asking what the new temperature will be. So you put 20 in there, and it says to the nearest degree. So obviously on a test, I would specify if I wanted whole number, decimal, I would have to tell you, obviously. But rounded, you see from the calculator, putting it in there, rounded, it would be 21 degrees. So 20 minutes, it's already below freezing. Technically, yeah, it'll be frozen by then. So here's an exponential growth model for population. So now we're going back to using, you see this model right here, not the Newton's law of cooling. Of course, in my notes, I have these problems before the Newton's law of cooling, but I'm not going to rearrange this now for that. So we have y equals ce to the kt. So we know there's 126,000 initially, so that means that's my c at time 0, and then 183,000 in 12 years. So that will help me get my k. So put the 183,000 for the left side for y, put in 12 for t, basically solve for k. I just canceled the zeros there, as you can see. You don't have to do that, but it makes it 183 over 126 equals e to the 12k, natural log both sides. So we basically have k equals natural log of 183 divided by 126 all over 12. So roughly, using 4 decimal places, 0.0311. So that means my official model now is 126,000 e to the 0.0311 t. So we want to know what will the population be after 21 years. So we put in 21 for t, and being a population or number of something, I would assume this, even though it didn't say, you would think this has to be a whole number answer, whether it's population of people or number of bacteria or whatever it is. It's kind of got to be a whole number. So I just took that answer, 242,107.5, blah, 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 and just rounded that to 242,108. All right, number 36. Same kind of idea. So we have 10,000 initially. So 10,000, y equals 10,000 e to the kt. So I need to be able to solve for k. So at, hard to read, but it would be, the population is declining here. So 4,000 will equal 10,000 e to the k4. So 4,000 divided by 10,000 is just 0.4. So we have 0.4 equals e to the 4k. Natural log both sides. So k would equal natural log of 0.4 divided by 4, which is negative 0.2291. So our growth model then, or technically this is a decay model, but negative growth. But y equals 10,000 e to the negative 0.2291 t. So when will the population be 2530? So we're solving for time. So I'll put 2530 on the left. And then, so I divide both sides by 10,000. gives me 0.253. And has the E negative 0.2291t. So we natural log both sides, kill the E. So you end up basically with natural log of 0.253 divided by that exponent, negative 0.2291. So you see I put the squiggly in there for approximation. Didn't ask for the nearest model, and I don't know exactly what answer that is. I guess I could put that in there at some point in time. I don't see a calculator screen, whatever I did, but so evidently it's roughly about 6 hours rounded to the nearest hour. Number 37, finding area between graphs. On these application problems, you can get the definite interval set up. You can use the like the F and Int on the TI calculator. That's fine. In a face-to-face class, I always ask that to show me the antiderivative correctly. I mean, show me the integral setup. Excuse me, just the integral setup, and then you can use the calculator to go straight to the answer if you want. So, but I did every one of these, working them out. I may not go through all the steps on those, but you could ask me if you had any questions. So it's always upper minus lower, so it's bounded between these two graphs. There's only one region here. Little thin section down there. And actually between 0 and 1, the y squared, and as soon as it goes past 1, that changes. But the x squared, y equals x squared, is the upper graph. So remember, in terms of x, it's always upper minus lower. It has nothing to do with the power of the coefficient. The power of the coefficient doesn't have to do with the numerical value of the power of the exponent. Coefficient has nothing to do with it. In other words, it doesn't matter that 3 is bigger than 2, is what I was saying. So x squared minus x cubed, because it's the upper function. So I did it the old-fashioned way. Did the two antiderivatives, subtracted, and you'll get 1/12. That's a pretty little sliver of area there. So 1/12 seems about right. So here's a picture with two different regions. So when two different regions where you have a different upper and lower graph, that means you have to write it as the upper minus lower, and then whenever it changes, you have a new upper minus lower. So you see I wrote from -4 to 0, the f of x right here, that one, you see I'll come around and follow it. See, it's the upper graph, and the line g of x is the lower. So it's f minus g. But from 0 to 3, it's the line becomes the upper, so it's g minus f. So this one, you're just taking a negative 6x minus a 6x, and everything else is the same. So you have minus 12x. And so it's x cubed plus x squared minus 12x. And the other one is just going to be the complete opposite. It's going to be negative x cubed minus x squared plus 12x. Now, you can put you can put this in the calculator, use technology, that's fine. Here's a little property. Now, whether you not use it for this problem, I find this property, I use it a lot in calculus, all the way through calculus. If I was doing this manually, I wanted to get rid of it. Anytime you have like a little extra negative out there and you want to get rid of it, you just if you reverse the limits of integration, just flip them over. Because flipping it over creates a negative, and then that would get rid of a negative by multiplication that you didn't want. Negative times negative would cancel. So now we have this set up. I didn't do this in the calculator, it looks like. Maybe I could find room and type those in there real quick so we could see, or you could try it yourself, obviously. Let me see if I have some other ones. Looking ahead here, see. No, did that one, but I do need to show this one. But these right down here, that's just working it out. Finding the antiderivative, plugging the upper lower, plugging in the lower number, subtract. I might just skip going through all the little steps there, because you can use your calculator at any point in time for that. Yeah, let's see. Minimize. Oh, that one's finished. Bring up. There we go. Should have already opened this up. Didn't think I was going to be needing it. Let me go back to this one. Let's see. All right, so I go math, a little bit newer calculator. The F and N's gonna, yeah. See, I saw did some of those using the F and N command where you had to type in the instructions of so the newer ones, operating systems do this, where it just puts the integral sign there. So now let me just toggle back and forth. So I'll go -4 to 0, and so I'll come in here and put in x cubed. Oh, no, no. Plus x squared, I believe. X squared minus 12x. Oh. Minus 12x. Dx. And I'll go ahead and just put these together in the same problem. Now, you see I flipped them over right here using that property just because I wanted to make everything positive. So I guess, or so I can type it like this, this form and go from 0 to 3, or flip all those signs and go 3 to 0. I think I'll just do that. So it doesn't really matter what you want, whatever you prefer. So I'll go 3, 0, and then I'll type in exactly what I typed in for the first one. And too busy looking ahead, so to focus in on whatever step I'm trying to do. X, there we go. Plus x squared minus 12x. Right. And let's see, x. Oh, let's see how we did. Nailed it. Might as well put that in there. Ooh, finding a place to fit will be the tough part. Well, I can shrink it down, then you can zoom in on it. want it. All right. Move that over just a little bit. Pesky equal sign won't move. All right, so slide that over a little bit, just trying to create a little room here. All right. Okay. Not sure how much I can expand this here, but it's a little bit better. All right, so you can do that. Now we have an x to the fifth bounded by x to the fifth, y equals 0, the x-axis, and between negative 3 and 2. So it's actually two separate, because it's negative 3 and 2, it's sort of changing over at 0. From negative 3 to 0, the y-axis, which is y equals 0, is above the curve. So it goes first, 0 minus x to the fifth. But then from 0 to 2, x to the fifth is first. It's before. So we have x to the fifth minus 0. So you can, I'm not going to retype these in the F&N, but do them manually if you want to. I did this just to let you know if you're looking at this way. If you don't care, go ahead and use the calculator. But see, that's a negative x to the fifth. So I did the thing I showed you earlier. I switched. Should just copy that down. Wouldn't hurt. There's space there. So let me. Yeah. So I use that property that created that negative, and we're in business. All right, never goes where I want it to. All right. Let's see. Okay. Yeah, I guess I'll put it right over here somewhere. Well, actually, right above where I did it would be good. I mean, right below where I did it. And we equal negative 793 over 6. That takes care of 39. Number 40. Now these trig functions, I always tell students that I would, unless I visually gave the graph, if I didn't give the graph, I would make sure that this was not, multiple regions, just one region locked in perfectly. So if you were not unable, you did not have the ability to graph this, you could sort of wing it by plotting points if you needed to. But since I'm guaranteeing that these are going to be just one region, if it's just one region, then that means one graph will be above the other one the entire region. So to know, and you can easily see that these connect at the intercept, 0, 0 is both of them. So they're connecting here at the intercept, they're connecting again at pi. So they're locked in. And to know which is the upper or lower without actually constructing the graph, if you do construct the graph in the calculator, make sure you use radians. And use values on the x-axis involving pi kind of makes more sense. So I think I used my x scale. In other words, my x scale looks like it's pi over 2. So it goes from 0 to pi over 2 to pi. Well, anyway, if you just pick some value between 0 and pi, plug it into both of these equations, you'll see which one is the higher y, therefore it's the upper graph. So evidently then that the, I'll use pi over 6 for example. Well, okay, well maybe not that. whatever the case may be. But anyway, the sine of 2x will definitely be the upper graph, and the negative 4 will be the lower. Of course, I guess another thing you could do is if you just did it in either order, yeah, since I'm guaranteeing there's only one region, if you get a negative answer, just change it to positive. There's f and n using the old school calculator. Here, antiderivative of sine of 2x is negative 1/2 cos of 2x. And then minus minus here makes plus. But then the antiderivative of positive, so that positive sine is negative cosine. So even though that changes to plus here, the antiderivative will make it go back to negative. And you just plug in pi, plug in 0, and we end up with 8 as our answer. All right. Now, oh, got a little Stewie head there. Doesn't have to be there. Let me get that right out of the way if I bugged you. I'll move him for a minute. I'll put it back in there. So we're trying to find the area of his head. Now, these, I don't necessarily make you have to graph these. It can be kind of tricky because, you know, the graphing calculator space is a function of x and y, but so it's to try to graph it, you can do it manually, but the fact that, so anytime you have x equals y squared and then x equals negative y squared, those are going to be sideways parabolas. The one that has a positive x squared will open up to the right, so that means the one starting over here at the origin, that's got to be the x equals y squared, and if it's got a negative in front of it, it opens up to the left. And when you integrate x in terms of y, see, with unlike when it's y in terms of x, it's always upper minus lower function, upper one minus lower one. This one is always right minus left. And like I said, if you get, and I never make these too complicated as far as multiple areas. So if you got it backwards, you just change the sign to positive. So and the limits of integration are now vertical, not left or right. So I did this algebraically, pretty easy. So I set the two equations equal to each other, and you get 2y squared equals 18, y squared equals 9. That's giving you plus and minus 3. So that's the lower and upper, and negative 3 to positive 3. So we integrate negative 3 to positive 3, the right function, which is 18 minus y squared, minus the left function, which is minus y squared. And you can do it manually. If you put this on the TI, you can use variable x, even though we're technically doing this. In other words, the calculator, it's just going to numerically perform the integration. It doesn't care whether you're using y or x. But when we set this up, we're not changing it from y to x in a mathematical context. But you can just put, you know, anything will go here. So if I go 18 minus 2x squared, even though, like I said, those are really y's, mathematically speaking, but it will integrate this exactly the same way. Okay. So might as well put that in there. And we have 72. Number 42, another one, y in terms of x. So like I said, if you just get, with only two regions, if you get them backwards, don't worry about it, because the answer will just be the positive of whatever you get, you know, if there were no other mistakes made. Another way you can look at this is, now this is a line in a parabola. So another way you can think about this without graphing is as I mentioned in the last problem, if it's a positive y squared, it will open up to the right. So then for these to have a nice region of integration, let me draw, I'll try to freehand something ugly again here. If that's going to the right like this, that means the line will have to cross through for to have a region like this. So that means in this case, so if the y squared is positive, the line will be on the right. Therefore, it will go first in the integral. In other words, it has to be the right function. So you see, look down here, I've got it first, y plus 4 over 2. It's the right one minus the y squared over 4. Now, algebraically, I solved to get the limits of integration. So you just set the two equations equal to each other. So we do a little cross multiply. 2y squared equals 4y plus 16. Bring it over, set it equal to 0. You can factor a 2 out of all that. And that turns out a nice factorable quadratic, which we want these to be. And you'll get 4 and negative 2. So obviously that means negative 2 is the lower. Positive 4 is the upper. So you subtract these two functions, and then so take the antiderivative, plug the upper number in, plug the lower number in. If you don't want to mess with all that, you don't have to. You can do the F and N like I did right here. And the answer is going to be 9 either way you go about it. So if you want to do it manually and have any questions, just let me know. So that takes care of part 3 of this video.